All right, so I'm going to talk a little bit about the sample mean, x bar, and how it follows the normal distribution when we have a large sample size. So we're starting with a random variable x, could be anything, but in this example, let's just suppose it's a student's GPA. So the population of student GPAs has a mean of mu. That's just some number. It could be 3.5, could be 2.5, could be 3, could be 3.2678, whatever it is, it's just a number. And it has a standard deviation sigma, which is also a number. Maybe that's zero point 0.5 or 0.47, 0.82. It's just a number. And for this presentation, we're going to pretend that you know what mu and sigma are. So whatever those numbers are, those values, you know what they are. Now, of course, in reality, this is not going to be the case, but we're going to assume it's so for the purposes of this presentation. So it seems reasonable, though, that if someone were to collect a random sample, let's say some GPAs from some students, randomly select some number of students, 50, let's say, collect their GPAs, then you might have a good idea, or that person might have a good idea about what mu is, right? They could look at X bar that they got from that sample and suppose or think that it's going to be close to what mu is. So in this context, though, might have some justification. Why would we think that x bar will be close to mu? Well, the fact is that x bar does follow the normal distribution with a mean of mu, so on average x bar will be mu, and a standard deviation of sigma divided by the square root of n when n approaches infinity. So as n gets very large, that's true. Now, in practice, though, what statisticians typically do is they're going to observe or, or proceed as though x bar does follow the normal distribution with a mean of mu and a standard deviation of sigma over the square root of n when x itself follows the normal distribution or when n is at least 30. So if we have a sample size of 30 or larger, it's going to be fairly safe, it's standard practice, to assume that x bar follows the normal distribution. Now, one thing to pay attention to here, or keep in mind as a warning, is that the standard deviation of x bar is sigma over the square root of n. And that's called sometimes the standard error, or people might refer to it as the standard error of the mean when we're talking about this for mu. So notice that sigma and sigma over the square root of n are not the same thing unless you have a sample of 1, unless n is 1. So something to keep in mind, if we had a sample of 1, of course, x bar would be the same as x. That's not typically going to be the case, and so want to recognize that the standard error, which is the standard deviation of x bar, is different from the standard deviation of the random variable x. So now it follows the normal distribution. We'd actually like to make it so that we're dealing with a standard normal, so convert it to a z. What was the process for doing that? We just take the observation or the value itself, in this case that would be x bar, subtract off the mean for x bar is mu, and divide it by the standard deviation, which in this case is going to be sigma over the square root of n. So in this context, if the sample has at least 30 observations, so 30 GPAs in our setting, then x bar follows the normal distribution, and when we make this conversion, which is we subtract off the mean and then divide by the standard error, we get a z value, and that follows the standard normal distribution. So with that, we want to think about what can we find out given different pieces of information. So if you know what x bar is, you can find z by plugging into that formula, because we're assuming again that we know what mu is, we know what sigma is, and n would be given as well. You could find x bar if you know what z is, just working backwards. Similarly, if you know what x bar is, you can find z. And now, if you know z, you can find the probability that some random variable along this distribution is less than the particular z you found. So this is something you've seen before, working with standard normal random variables. So you can find that. That's the same thing as a sample mean being less than your x bar. Why? Because you used the x bar to find the z value. So in Excel, you would just use the norm.s.dist function. You can also work in reverse then, as you've seen before. If you happen to know what the probability is, you can go backwards and find a z value or an x bar and find those pieces. How do we work backwards? In Excel, use the norm.s.inv function, and that would give you the resulting value, z. So hope that helps a little bit, and I'll also give some further examples in a separate video.